did we do last time? We talked about noise. That's what we finished up the lecture on. And we learned that in the physical world, because our antennas are surrounded and are themselves not at absolute zero, they're always receiving energy, noise energy. These are basically photons, black body radiation photons, being belched in all directions by all objects that are not at absolute zero. And it slowly washes over our antennas, continuously changing from one moment to the next. And the end result is that if we look at the terminal voltages of an antenna, even if we're not transmitting anything in that antenna's bandwidth of operation, we will see this random noise signal come out of it. And we talked about the properties that of that noise signal last time. Recall that if we looked at it on the spectrum analyzer, in the frequency domain, we said that over the RF bandwidth it would look like a sort of a flat, what we call white Gaussian process. This flatness in the frequency domain means that each sample in the time domain is completely uncorrelated. So you think of this as sort of like the power spectral density of noise. We call it S sub n as a function of f. Power spectral density for our noise signal. And of course, you never see this on the spectrum analyzer, because spectrum analyzers do only real signals. And real signals always have symmetrical power spectral densities. But of course, mathematically, we know that there's this other part over here in the negative frequency domain to get all the math worked out the way we defined power spectral densities and Fourier transforms. Now, we said that, of course, most of our signals in wireless are band limited. They're centered at some sort of carrier frequency, F sub c. And of course, we got the mirror image going on the negative frequency side. And so there's going to be a desired signal in this band that we want to detect in the presence of that noise. So what we typically do to figure out exactly how much noise power is in there, we said last time that we used the equation B n naught, where n naught over 2 is sort of the level of the power spectral density noise metric. And we said that we can also calculate this as B Boltzmann's constant K times the physical temperature, the average temperature that the antenna, quote, sees in its environment. And we said this has units of watts and can be used, probably one of the most important parameters in a system that isn't limited by interference, because this determines your carrier to noise ratio. You take your received power, you divide it by your noise power, BKT, or KTB. Usually put Boltzmann's constant first. And this also often tells you the limitation of the fundamental limit with which you can transmit information, because it's basically going to be a measure of the quality of your signal power and the disturbing noise that's going to corrupt it and keep you from decoding that signal. Now, a couple of notes before we get into our noise figure analysis. One thing I didn't mention last time is that this analysis assumes that you have like this perfect brick wall filter that you can drop your signal plus noise through and get rid of all of the out-of-band noise. Now, of course, anybody that's ever tried to build a real filter in real life, outside the world of MATLAB, would realize that a causal filter can never look like this. In other words, a filter that basically has no latency to it and doesn't basically have a response for t less than 0 when the signal can't anticipate the signal hitting it. You can't have a perfect brick wall. In fact, usually, you got something that's kind of ripples, and then it's got a smooth transition and some more ripples out of band. And so oftentimes when you talk about noise analysis, that B that they talk about is not always the physical bandwidth of the system. or of the signal. It's what they call the noise equivalent bandwidth. You'll see that term used sometimes in the book. And that just means that, okay, I've got a filter response that this noise has to pass through. And as soon as you pass a additive white Gaussian noise through a filter, it no longer has a straight line for its power spectral density. The power spectral density of the noise will be sort of like take on the characteristic of the filter. It'll ripple as a function of frequency. And so how do you calculate the area or the wattage? You integrate the area under the curve. And they basically say, well, you know, if the noise level was sort of an n0 over 2, if it was flat, and I had an equivalent bandwidth, B equivalent, what is the width of that bandwidth so that the area under this curve would be the exact same as the area under this curve? And then that's what they call the noise equivalent bandwidth. The bandwidth that basically allows me to approximate it as a flat noise power spectral density and pass it through the system with my KTB type equations that assume flatness. In our class, whenever I ask you a question, or if I say something, unless I say otherwise, we're always going to assume that we have these perfect filters and that your noise equivalent bandwidth is effectively the bandwidth of your signal. If it's a well-designed system, it's never that far off. So that's what we're going to. That's just a side note, because you'll see this in the literature. If you ever see that, they're really talking about all the stuff that we're talking about. They're just trying to, adjust the bandwidth just a little bit to account for some of these non-idealities. So that's point number one I wanted to make. Another point I wanted to make, and this happens a lot in satellite communications. Remember, for that carrier to noise ratio, we said the top is the link budget. G sub T times G sub R times my transmit power, antenna gain for transmit, antenna gain for receiver. Let's see, what else do we put up here? We got a lambda squared. We got 4 pi r quantity squared. And this is my receive power in my link. And of course, my noise power is going to be K, Boltzmann's constant, times physical temperature, times the bandwidth of the system. And of course, this is received power over noise power, one of the most important metrics of quality in a communication link. Okay, so let's say I've got a fixed signal that I want to transmit. I've already established its bandwidth. I've transmitted it, so it's gone through my antenna. I've got a certain distance that I want to traverse. At the receiver, what are really the only two quantities that we actually have control of in this equation? Our bandwidth is fixed. Transmit power, transmit antenna gain is fixed. R is fixed. I got a frequency operation, so lambda is fixed. The only thing I can change at my Earth station with a dish would possibly be these two quantities here. And so what we're going to do today is, first of all, we're going to talk about once the noise gets into your system, we're going to add some noise to it. And so this T sub P is actually going to become a system temperature based on all the possible sources of noise. And this GR over T sub S, this ratio, is actually a really good metric of how good your receiver is. Because all the other stuff you really don't have control over in a link. If you're using an established protocol and you've got an established application where you're going to have this much distance between you. And so a lot of times when you talk about, especially on Earth stations, they say, how good is the Earth station? They'll say, what's your G over T? What's your linear gain of your receiver antenna over the physical temperature of your receiver? And that'll be a really nice metric, because the higher that gets, the more sensitive and the longer distance you can make your link, the better the decoding will be if it's a digital link. And so when you talk about the G over T of like a cell phone, you'll be lucky to get like 1/100th, out of this thing. Because the receiver antenna gain is probably about 0 dBi. It's pretty crummy. You'll be lucky to get isotropic gain on average out of this thing. And then the receiver sensitivity is pretty low. It's going to be like 200 Kelvin. So what is that? 0.5%, 0.005 G over T. Terrible. But then you go to some of these really big radio astronomy dishes that have extraordinarily high gains, tens of thousands, hundreds of thousands in the linear scale, and really low temperature. They're pointed towards space. Their beam is pointed into the blackness of space, and they use some really nice RF electronics. Some of them will even super cool their electronics so that their devices are operating at a very low temperature. Those G over Ts are, extraordinarily high. You measure it in the dB scale, we could be talking like 50 dB, 60 dB for a really giant dish with some sensitive RF front ends on it. So just be aware of that terminology, because you'll see that again in satellite systems. So okay, we said we got this noise. It's coming through our system. What do we talk about today? First half of the class, we're going to track noise through the system and talk about how devices can add to it and how to characterize an aggregate system with the system temperature. This will be related to the noise figure of your RF front end. And then when we're done that, hopefully we'll have some time to get into Doppler shifting, which is another channel effect in our satellite system, and one that we don't normally worry about for terrestrial systems because stuff doesn't move that fast. But we're going to see with a couple of examples that in satellite communications you can actually get a significant Doppler shift in the data that you're actually sending. So that's sort of the outline for today's lecture. Okay. So the question is, what does the RF chain look like after this signal plus noise has made it into my antenna? So if we draw it in terms of block diagrams, here's my triangle with the stick coming out of it. That's the symbol we often use for generic antenna. I guess it looks like a hobbyist took a coat hanger and turned it into an antenna. What's the first thing any RF engineer does after a receiver antenna? Power amplifier or low noise amplifier. That's one of the steps. There's probably one other thing you want to do before that. This is bandpass filter. That's right. That's right. You can sometimes get away with LNA, but a really good RF designer will always put a bandpass filter as the first stage. And the reason why that is this is actually not necessarily to clean up your desired signal, because you can do that later on in the RF chain, and you can do it better. What this here is for is to knock out any out-of-band interference. Even if you're going to filter it by passing it through subsequent stages of bandpass filtering later in the RF chain, it's important to knock out any nearby interferers that could possibly be leaking through your antennas, because the next stage is going to be that low noise amplifier. LNA, low noise amplifier. And because it's an amplifier, if you've got a lot of signal energy coming in here on the input, you could conceivably saturate this thing, even if you didn't intend it, even if there's some out-of-band energy. So for example, let's say I've got a 915 megahertz wireless LAN. I've got maybe my laptop, and it's got a little card connected to it. Normally we use 2.4, but there are some that work at 915. And I've got a cell phone that's still using one of the 860 megahertz channels that are transmitting voice and control channels. And I get those close to one another. Let me say, later on down the line, we're going to put a nice bandpass filter here. That, on the RF chain of my Wi-Fi card, that should knock out whatever signal comes out of here. Because, they're about 60 megahertz apart, roughly. So, okay, everything's going to be fine, right? But so wait a second. remember, this receiver here is trying to receive a very, very weak signal. And I've got a signal here coming out of here, which looks maybe like 23 dBm, 25 dBm, something around that category. And remember, what comes into here is probably like neg 90, neg 80 in some instances. So even if that I lose some signal energy from cell phone through the antenna and through some of the devices, when that really strong signal hits that first amplifier, it could drive it nonlinear. And once that LNA goes nonlinear, any desired in-band signal that you put through there is going to get severely distorted and clipped. And you're probably going to lose it completely through your chain. So we do put a filter on here, and we have to be careful. It's usually a crummy filter. It's kind of a, the goal is just to attenuate 10 to 20 dB anything outside of your desired band. Because when the cell phone gets close to the receiver, 1 meter of path loss is so much less than the 100 meters or 10 meters of, card to access point that has to be communicated, sometimes with obstructions, that it can really overwhelm your amplifier, even a relatively small transmitter. And if you have a variety of those sources around, that's why this is one of the most important things to put on your RF front end. Then you can get into the LNA, and then you can clean it up later. This can't be too good of a filter because there's this theorem in filter design basically says the tighter that you want it, and the higher the Q and the tighter the filter characteristic, the overall lossier the filter gets. The insertion loss goes up. And so that's you got to be careful with, because as we're going to see, this is the one place that you don't want to lose any signal. And so recognize that this is here, but it doesn't really add that much to our system. We're going to presume that it goes cleanly through here, and we're going to take it out for our initial analysis. Alec?
Yeah. I know band passes need to be tighter for terrestrial commercial grade stuff, because you've got plenty of other systems nearby in the frequency in the spectrum. But the homework problem, if I recall, was 27 gig, right?
The homework problem from homework number 3?
Yeah, the most recent one.
I forget the exact frequency that I asked you.
It was up near 30. I'm certain of that. So there's nothing else common near there, right? So in other words, the question is, you can make it wide, right?
You can make it wider, probably. The question that Alec is bringing up is that you generally make this filter tighter for terrestrial receivers because they operate closer to the ground, and there's more stuff and traffic around here, more potential for somebody to kind of walk by with their wireless transmitter in their pocket at 1900 or 900, or there's more chance of getting a Wi-Fi transmitter close to it. And that's true. You would tend to want this to be tighter at the lower frequencies. But there are actually a lot of millimeter wave applications out there, like trunking from cell tower to access point that are floating around there. And you don't want to, and there are also some spatial users, reuse of frequency, and side lobes on your dish that'll pick up other satellites using those same channels. So there are some sources still in satellite, and you still want to keep a nice front end on your receiver before your LNA. So you're right, it's not quite as much of a problem in some bands, especially when you go really high in frequencies, but it's always a good practice as an engineer to put that there. Yeah, Grant?
Licensed 10 gigahertz area or the ham area, and so you always might not have active transmitters there, but won't you always have people who have harmonics of whatever system they're using?
There is the potential for harmonics, although probably the harmonics, hopefully, if they're not violating any FCC regulations, the harmonics themselves will be pretty low compared to the actual transmit power that, say, the 10 gig receiver is transmitting. So the worst that they'll probably influence the system is in-band interference. Like they'll shoot a harmonic up into 30 jigs, and maybe you got some sort of satellite link that works at 30 jigs. And then that'll be part of your signal-to-noise ratio. You got to step up that noise power for that. The harmonics generally are less of a concern for this front-end filter here that would go in front of your LNA, because they're generally not strong enough to force this nonlinear. That's really the only thing that this filter is trying to do. Keep this from going nonlinear with all the other stuff that's out there.
But like the mixer is a nonlinear operation and the mixer is a nonlinear operation. So if like something is like at 10 gigahertz and for 5 gigahertz, it still can be a problem. Because it can mix it with some harmonic of the local oscillator and can still come into the band after the mixing.
That's true. That's true. Generally, though, you have another bank of filter. If you were concerned about that, you could put a filter later on to knock that out before you do your mixing operation. So it depends on your application. If you anticipate, his question is basically, okay, and this is a good point. This is something you always have to be aware of in RF design. Let's say I have a signal spectrum up here at F sub C. And remember, it's like the fourth day of class, we talked about a transponder and how you mix signals down. And we're going to eventually want to do that here in our receiver chain. So if you have some harmonics, some harmonic content up here, and when you go to mix it down, you basically multiply it by cosine that shifts it down and then shifts it down. It could be, because you're shifting two ways, you could actually wind up with some of this stuff, if it's in the right distance away from the carrier, to shift into the band, what's called your intermediate frequency. So if you imagine there's a whole bunch of, say, harmonic stuff here. Let's just draw it all over the place. That's kind of how it is sometimes. And you mix this down by shifting copies of it down. Sometimes, if this is your target frequency, this is going to go down here. But then some of this frequency content here is going to go up here. And now they're both in band, and you can't filter it out. So one of the tricks to picking out a local oscillator frequency is trying to pick one such that there's a quiet band that same distance away on the other side of the frequency spike in the frequency domain. So like if you're mixing 12 gigahertz down with a 10 gigahertz LO, we'll make sure that there's nothing at like 8 gigahertz that will mix into the band, that it's relatively quiet. If you're really concerned about that, you can put a nice tight filter and notch that area out. But you would generally want to do that a little bit later after your LNA when you've cleaned the signal up already. So the purpose of this one is just to give you enough filtering to keep this device from being nonlinear. Okay, so we put LNA, maybe another filter, but I'm not going to put my filters in at the moment. Maybe we put another mixer here, mix it down to a lower UHF frequency, and then another just amplifier. So we have an RF chain like this, and we're kind of gradually amplifying and stepping the signal down to low frequencies. Local oscillator feeding that mixer. Okay, so my signal comes in here. It's got power and it's got noise. And when it enters into the LNA is an active device. It's got these biased transistors in it that are being used to amplify the electrical signal coming inside and then leaving. And because it's an active device, and it's got warm components, and it's biased, it's got these junctions that are statistically combining and recombining holes and P's and all that. I mean, we have a couple of semiconductors guys here that probably deal with this stuff on a regular basis. Do you measure like noise temperature of your devices? Quite a bit. So every device has some sort of noise associated with it, especially an active device. This is additional Gaussian white noise that will be added into the signal in addition to what has already gone through it. So the physical noise that comes in through the temperature of the antenna, that the temperature temperature that the antenna sees will combine with this device noise, and so the output will be basically even noisier than what you started with. So the device model that we typically use for this let's look at our front end here. Antenna. We're going to model that amplifier, the effect of it on our system, as an additive block, a unit that's going to give us some sort of gain, GRF, and then it's going to have some sort of output. And the amount of noise that gets added in here, we like this model of K physical temperature times bandwidth so much, and it works so well for describing roughly what is white noise that gets added in as a device temperature, that we usually just use a temperature to describe the device, T sub D. So think of this as noise power, K T sub D times my bandwidth of my signal is going to be added into the signal at this point. And we typically put it in, define it to be before the block of gain. So what comes out of here, if this is PR naught going in, PN naught going in as well, receive power and noise power, what comes out is basically my PR naught, my desired signal power, times a certain amount of RF gain. And what comes out as noise on this terminal is basically my GRF times my original physical noise power. Of course, it goes through gain. You can't basically, if this is in-band noise power, you can't add gain to your received desired signal and not add it to your noise power, plus K T sub dB. Boltzmann's constant, device noise temperature, and the bandwidth. And so notice that the carrier to noise ratio will never get any better than it does at this point, because this is always going to have the same carrier to noise ratio through the amplifier, excluding any device noise that you add to it. And then you're going to kind of add the device noise, so it's always going to degrade your carrier to noise ratio. Amplifiers are kind of like a rising tide. You know, all the distance between the deck of the ship and the water is always the same, right? If anything, it's going to get sunk because a little bit of the water is going to splash into the ship as the tide rises in that amplifier. That's effectively what the device noise is doing. And it's going to weigh the ship down. And hopefully, it's still not to the point where you will sink the ship, which is getting effective in our analogy to getting a carrier to noise ratio that's so low you can't even detect the signal or the information on it. So this is the basic model that we use for describing how a device adds noise to a system. So what would the carrier to noise ratio be at this point? CNR is equal to GRF over PR naught, my original received power, over GRF PN naught plus K T sub dB, bandwidth, device temperature, Boltzmann's constant. GRFs cancel, and you get basically PRO over PNO times Boltzmann's constant, device noise, bandwidth. this was our carrier to noise ratio before it hit the amp. This is what it is after it hit the amp. Clearly it's going to be lower because this is always a positive number. Okay, so let's go back to this pane over here. And look, we've got multiple devices through here. Each of these devices is going to have some sort of gain associated with it. So let's call this, G sub RF. This will have like G sub M. Call this a mixer. And let's see, what else do we want to add in here? So we have another amplifier, so we'll call this GIF. Mixed it down to an intermediate frequency. And each of these devices is going to have device noise. So let's call this TRF. Let's keep our subscripts consistent. A device temperature in kelvins for the first amp that adds noise into it. Device temperature for the mixer, T sub M. And a device temperature for this amplifier here, T sub IF. So based on our noise model, how does the carrier to noise ratio degrade as it goes through this system, as it marches through our electronic chain? Well, signal power received signal power is basically going to be our PR naught, the power into our antenna, and there's going to be some gain for the LNA, some sort of gain for our mixer. And keep in mind, when I say gain, if it's mixers aren't really intended for gain, so this could actually be a number in the linear scale that's less than 1, right? Gain less than 1 is really a loss. GIF. And then for our noise power, P sub noise is going to be Boltzmann's constant times the physical temperature that my antenna sees, T phi, times the bandwidth of my system. And of course, that is at the very front of the system, so that's going to go through the exact same set of gains that our desired signal sees, because it's going to go through the exact same devices. After the first antenna, recall, okay, antenna here. After the first antenna, we're going to go through that low noise amplifier. And we said that in our noise model, we take the physical noise of the device, add it in, and that's actually before it experiences the gain in our convention. And so added to this is going to be Boltzmann's constant times the physical device noise of that LNA, which in our previous diagram we called T sub RF. That's going to be multiplied by the bandwidth of our system, and it's going to experience the exact same gains that the physical noise experienced. And then the next stage is going to hit, that's the mixer. And the mixer is going to add some noise to it. D sub M is going to be the device temperature in kelvins of that mixer. But the mixer hasn't experienced the gain that the LNA has provided. It only experiences our G sub M and what we call GIF, the stage of that next amplifier. And so we can write this as K. The noise that gets added at this point is K, T sub M, times a bandwidth, times not GRF. It's already past that device. It only experiences the gain of the mixer and the gain of the intermediate frequency amplifier. And then, of course, the last stage, you get to the intermediate frequency amplifier. And that also adds device noise, but this noise has not gone through the same two gains previously. So this is just going to be K T sub IF, the device noise in Kelvin, noise temperature for that device, times the bandwidth, times the IF gain. Well, as you can see in this treatment, there's a whole bunch of common terms. And we can just group them together. In fact, this is how we're going to group them. We're going to group them in a special way. P sub n. There's a K, a Boltzmann's constant, and a bandwidth commonality factor that's in every single one of these terms here. But you know what? I'm going to go ahead and factor out all of our gains, too. So it looks kind of like this up here. G sub RF times G sub M times G IF. And when I factor all that out, you see what I'm left with here on the first term is a physical temperature. Makes sense? That's physical temperature of your antenna. Second term is the physical temperature of the low noise amplifier, TRF. Now, the next term, because it's the temperature of the mixer, and because RF doesn't show up there, I've got to take that temperature and I've got to divide it by GRF. Likewise, down at this IF amplifier, I don't have GRF or G sub M, so I just got to divide it by both of these if I want the math to work out, my factorization of these three gains. So,
This must be TM. Shouldn't it be
TM, yes, thank you. Okay, so look at what's happening here. First of all, I have something in here that has units of temperature. All this stuff together is actually what we call the physical temperature of the system, T sub cis. A temperature in kelvins that collectively represents how the entire system, my antenna, my amplifiers, my oscillators, my mixers, my whatever device is interacting with my RF chain, how that effectively adds noise to your system. So a lot of times when you're speccing out a receiver for communications, this is one of the most critical components that you want to read off of it. What is the T sub cis? And a lot of times the T-sys won't include the physical temperature because it doesn't make presumptions about where you're pointing your dish and where you're operating it. It might just include these terms here for basically how much noise your receiver adds into your signal. Brad, do you have a question?
Yes. Is there a reason the first term doesn't include the gain from the antenna?
That's right, because typically the question is, why does the first term not include the gain of the antenna? And it's just a sort of semantics. The way that they define that noise figure, or that amount of noise, is with a temperature as measured at the port. So sort of the gain is all kind of included in there. If you think about it, if you didn't do that, the problem would become very hairy, right? Because it depends on where you point your antenna, and you've kind of got to integrate over the whole pattern, right? It's like if the main beam sees a hot spot, you got to take that gain and weight it against the hot spot. If the side lobes are pointing off into space, and you kind of got to weight them spatially against the non-hot areas of space, and so forth. And so it winds up being kind of rules of thumb anyway for that number. You say, oh, you're operating on Earth, you're pointing to the sky with a fairly directional antenna, physical temperature of 120 kelvins. You know, you kind of read that off the book. But you're right to notice that that does not include the gain of the antenna. So yeah, this is your system temperature. Now, in this class, unless I tell you otherwise, this is an engineering class, so we're very into being practical, right? When you're speccing out a receiver, one of the reasons why we use an LNA instead of just an A on the very front end is because that's where it's critical to clean up your signal and give it the highest possible gain you can and add the least amount of noise. And in fact, that adding the least amount of noise is even more critical than the gain, which is why most LNAs, if you buy them, they will have lower than average amplifier gains in that block of amplification. What the designers of that device are really after is a device that will add as little noise as possible to your very sensitive and weak, easy to corrupt RF signal. So in this class, unless you're told otherwise, if you have a good LNA, your system temperature is approximately equal to those first two system temperature components, your physical noise from the antenna and the LNA device temperature. Why? Because if it's a good LNA and you're getting at least 10 dB a gain, 20 dB a gain, something in between there, then this is going to be a large unitless number, G sub RF, in the denominator. And whatever this is, it's going to not contribute much to the total sum because it's getting knocked out. And presumably, if you have some more amplification, as long as you have additional amplification, you're going to consistently knock these out further and further and further. Think of what would happen, though, if you didn't have that LNA on the front end. This term wouldn't be here. I wouldn't get G sub RF. And my next in-line device would be a mixer. Maybe it has a noise temperature of, I don't know, 30 Kelvin, 40 Kelvin. Maybe it's not that much. But loss here kills you. If G sub M is less than 1, then it amplifies the effect of that device noise instead of contracts it later on the RF chain. And so that's why that first device right there, it's got to have some gain, and it's got to be TRF as low as possible. And that's what we're always after in design. That second amplifier down here, man, that could be a really high number. It could be, 200 Kelvin, 500 Kelvin. Doesn't matter because it's getting killed by some of these gain terms in the denominator. So it's always that first component that's sort of the bottleneck in sensitivity. Yeah, you have a question?
Talking about that, is there a good idea to have a band-pass filter after LNA, because band-pass filter will have some loss, and so that will increase your overall noise figure of the system?
There are some instances where you may want a bandpass filter after your LNA. And I forget, what is your name?
Hubert.
Hubert?
Yeah.
Hubert brought up a great point about making sure that before you do your mixing operation, don't mix things into your signal. So that's not a bad thing to do, and it's certainly much better to do after your LNA than before your LNA. So if you need to do it there. It's going to be kind of system dependent at that point, though. Depends on what spectral real estate your signal is occupying. If it's in a noisy part of the world where you've got you got to worry about out-of-band stuff mixing in or some other effects like these non-linearities. But you're right in that if the filter is lossy, if there's a filter in here that's lossy, then any noise that gets added in at that step or subsequently will be amplified will be effectively amplified because of the loss of signal power through that device. Okay. Pretty straightforward. One thing that you should be aware of is that sometimes when you see a device, it will, instead of quoting your noise figure, or excuse, instead of quoting a device temperature, it will quote a noise figure instead. I've got a sample spec sheet I'll show you in a second. So NF is a unitless value called noise figure. And sometimes it's reported in dB. And to convert it into device noise and use it in our system of equations that we developed over there, to convert it into device noise, you take a reference temperature, and multiply it by noise frequency, noise figure minus 1. So the reference temperature is, unless somebody tells you otherwise, the standard reference temperature that everybody makes noise figure measurements with is 290 Kelvin. It's approximately room temperature in the human world. So the way that a noise figure measurement is defined is basically at 290 degrees. I got 290 degrees Kelvin, or I have 290 Kelvin of noise coming through my system. Noise figure you can think of as basically how did that noise get magnified by the device temperature. So if you were to rearrange this equation, for example, you would basically get T sub D plus T sub naught would be equal to T sub naught times noise figure. So I take this much noise and I put it into my device. I got this much added in terms of noise device temperature, and that's effectively like amplifying the original noise that I had. So you always have to specify a reference temperature to describe this noise figure term, the way that noise is amplified through a system. And if you do that, then you can convert easily from one to the other. But engineers like that noise figure term too. In fact, TD is the device noise of the device that you're measuring. So, for example, noise figure is usually characterized. You can actually do noise figure for an entire system, and in that case, T sub D would be T sub sys. But a lot of times when you have just a single block, an amplifier, for example, you'll look at the spec sheet and it'll say noise figure of 3 dB. It's 6 dB. Let's make it a little more realistic. So that means a factor of 4 in the linear scale. And what that means is that for 290 Kelvin of noise coming into that device, you'll basically magnify that by a factor of 4 on the output. So it'll look like, close to 1200 Kelvin, between 11 and 1200 Kelvin on the output of that device. And so it's targeted specifically for the device as a device parameter. Let me show you an example of that. I have some overheads I printed off the web, some common amplifier specs. And I'm not even sure if my print is big enough to be seen, but let's go ahead and try. I'll read it off to you if you have trouble seeing. Okay. Oh, yeah. Oh, this might be too small. Oh, that looks better. Okay. Well, I'll read the numbers off that we see anyway. Here is this high isolation amplifier. I went and logged on to minicircuits.com and printed out this spec page. And you can see that it's got a whole bunch of specs here. There's actually a couple different models. And it kind of teaches you how to read a general spec sheet for hardware in RF. Different model numbers, different frequency bands. Most of these are about from 0.5 gigahertz to 2.5 gigahertz, so they're fairly broadband amplifiers. This is the voltage that they take. Let's see over here. We've got some 1 dB compression points. This kind of tells you where the amplifier is going to get nonlinear on the output power once you exceed 17.1 dBm. If you can read that, that means that the thing is going to start going nonlinear. That's about 5 milliwatts. No, excuse me, 50 milliwatts. So, and you'll notice in this column, here's noise figure, measured in dB. So they've taken 10 log base 10 of the quantity we've put on the board. And it's measured at 1 gigahertz, sort of in the center of its bandwidth of operation. And I see a value of 5.4. So that's going to almost quadruple the amount of noise if you have about 290 Kelvin going into your device, into this amplifier. 290 Kelvin in, about 1150 going out, 1100 going out in terms of Kelvin. Then you multiply by Boltzmann's constant and the bandwidth of your system to get the amount of watts of noise power. Then you could track the carrier to noise ratio, and then when you get down to baseband signal to noise ratio through your system. Pretty straightforward, right? Here's another one. And this truly is a low noise amplifier. And of course, what's the trade-off here? Money. Expensive. More costly. I didn't... Oh, here. We do have cost figures to compare. This one is $120 for one amplifier. And this one costs, let's see. I don't see a price. Oh, here over on the side. $60. Cheaper. So that one was $60. This one is $120. And you know what? You're not even getting as much gain, I don't think. Well, no, the gain's not too bad. The lousy maximum power. Notice the 1 dB compression points are about 10 dB less than the previous one. So these really aren't meant to put out a lot of power, but that's okay. You just need to get gain, and you need to get as little noise added as possible. What's the noise figure of this one? Let's see. Noise figure 2 dB. Less than doubles the amount of noise. So if you put 290 degree or 290 Kelvin noise from your antenna into this device, it would be maybe like 400 Kelvin on the output of total noise. So anyway, gives you some ideas about how important that parameter is and how to read it off the basic spec sheets. Any questions so far? No? Perfect understanding of noise? My carrier to noise ratio of my audio coming out of my mouth is very high today. That's encouraging.
What about internal noise? Like you have a power supply nearby and it's getting into your line. Where's that quantified on this?
Oh. The question is...
Your amplifier stage is
Yeah.
earlier line.
So the point that Grant is bringing up with is a good point. Whenever you do a realistic signal, a realistic system design, there are all sorts of noise that get into your system potentially. So what we're tracking is basically, even if you have the world's most perfect environment, the world's most perfect EMC environment, electromagnetic compatibility environment, where basically that's the study of how to kind of keep the noise from the world and from other undesired points in your system from getting into other points in your system. Even if that's perfect, we would still have these device noises and physical noises. Now, there's this other effect where, if you have a system and you've got baseband circuitry, intermediate frequency band circuitry, RF electronics on it, and all these other components, and they're connected to each other, whether they want to be or not, through signal lines and also power supply lines, because all of these require devices that draw off of power supply. Then there are actually these weird pathways, and sometimes it's just pure radiation. A signal trace will radiate a little bit of its energy, and it'll jump to another board in your box and fold into your signal that way. Or sometimes it'll go through a power line trace and enter in. And I don't know if there's a really nice way to analyze that and characterize that like we've done up here. Usually you assume it's 0, and then when you implement it, you find it has popped up somewhere, and you just try to get rid of it. In other words, you never plan for it. You assume that the microwave engineer has done their job and kind of isolated everything and kept the noise away. That rarely happens, especially on prototypes, but Usually that becomes such an ad hoc problem. You throw the academic stuff like this, what we're doing, out the window, and you just try to get rid of it. Try to track it down. Any other questions? Okay. Let's switch gears. Talk a little bit more about another channel effect. Really, the introduction of all that EM theory is basically giving us a platform with which to discuss the wireless channel and all the bad things that can happen in it. So the next thing I want to talk about is Doppler shifting. So here's our satellite in space. And he's transmitting a signal. Looks like a spherical wave, but eventually when it gets to Earth, it's a plane wave. And of course, if it's a plane wave, we know how to describe that mathematically. Electric field of that plane wave, phasor, as a function of space, is equal to E naught times some polarization. Let's assume the phase is 0, exp minus j k hat dotted into my position vector. That is how we EM people like to think of the electromagnetic wave, as a function of space. We've taken the time dependency out. However, COM people like to think of the channel in terms of time, because really the channel is like a black box to them. It's the temporal effects that it introduces on a time-varying signal that are what they really want to capture. And so in this case, let's say we have simple motion. Instead of a dish antenna, we've got some sort of handheld unit, say, and it's moving. It's got a velocity vector. It's a vector because it's got to have a speed in meters per second and a direction of travel. And we know that in simple motion, your position vector, your point of observation r, which of course would be x, stick it on the x, y, stick it on the y, z, stick it on the z hat unit vector. The vector that tracks position is going to have some sort of initial starting point, and then it's going to change as a function of time. Basically, your velocity vector times the scalar time added on there, and that describes our simple linear motion over a short period of time. And so what I can do is I can take this and I can plop it into there and see what happens to my plane wave. How does this antenna view the plane wave as I start moving through space? Well, now my phasor becomes E naught, polarization vector exp minus, let's see, I got j k hat dotted into this thing, a starting point, plus scalar time times velocity vector. I'm going to take my scalar time and put it up here. And so what I have left is k hat dotted into my velocity vector. You know what? For simplification, I'm going to say we're starting out at 0. The 0 vector. That's our starting point. And now I just have this expression. Okay, so when I put this back into the time domain, let me do that. My E field which should be proportional to the voltage across the terminals of my antenna. Remember, this is volts per meter. As a function of what is now time, how do I convert it back to the time domain? I take real value E vector exp j 2 pi fct, my carrier frequency fc. And I plop this expression in for my electric field. It's really just an amplitude, a polarization vector, and this time-varying frequency offset. So these exponential arguments are going to add together. When I take the real value, that's just going to make the cosine. And I get E naught, E hat, cosine 2 pi fct plus k hat dotted into velocity vector times time. Okay, let me clean that up a little bit. The electric field on that antenna, and hence its subsequent voltage, is going to look like an amplitude, polarization, 2 pi. I'm going to factor a term out here. F sub c, my carrier frequency, plus k hat dotted into velocity over 2 pi, because I factored out a 2 pi here, times time. And so from my temporal perspective at my receiver, when I am in motion, when I have non-zero velocity vector, what effectively looks like, it looks like my carrier frequency just changed. It shifted. And so we often call this term here the Doppler shift. And notice what it depends on. First of all, there's a hidden frequency dependence in here. This is wave number k, right? Radians per meter. 2 pi over the wavelength. In fact, if we wanted to, we could put the 2 pi over the wavelength term in here. 2 pi divided by wavelength. And the 2 pi's cancel. As frequency goes up, wavelength shrinks. Wavelength is in the denominator of my Doppler frequency. What happens to Doppler frequency as my carrier frequency goes up? The shift gets bigger. The moving at the same velocity will shift the Doppler frequency higher. It's also proportional to my velocity. So the bigger my V term gets, the bigger my shift should get. That's not really surprising. But it also depends on direction. In fact, the Doppler shift can be in 2 different directions. If my velocity of motion, oh, and I have to be careful here. This should be a minus sign, because I had a minus over on my other term. So does this make sense? Does the minus sign make sense? If my wave is traveling this way, k hat, that's the direction of wave propagation, and my velocity is heading into that, what this is saying is that, okay, the dot product of 2 opposing vectors is negative. Negative, a negative means I get positive Doppler frequency. As if I'm, okay, so this is almost like listening to a NASCAR race, right? Acoustics obeys Doppler shift rules as well, depending on its wavelength and the velocity of things. And of course, from your perspective, if the car is in motion, when it goes by you, it's got a constant hum if you're like sitting on the hood. But if you're in the stands and the car is moving with respect to you, when it's coming in your direction, the Doppler shift is higher. The pitch goes up, right? And then when it passes you, it goes down. So if you were sitting on the hood, it would sound like this. But from the stand, it's right? Because that velocity vector is changing, going from positive Doppler shift, negative this term, to negative Doppler shift, which is a positive this term. Wave and direction of propagation are traveling in the same direction. Now, normally, I said we don't usually worry about this in wireless communications, but you have to be careful with satellites because satellites are moving so fast. So, let's see. Let's put this in terms of our geometry here. We derive this in terms of the receiver position. We said, oh, let's say we had a fixed transmitter and a receiver that was moving. But you know, in satellites, of course, this is going to have to be moving too. So it leads to the interesting case where you could conceivably have a transmitter and a receiver that's actually moving. So let's come up with a general equation to describe that. Here's our velocity vector for our receiver, v sub r. Here's a velocity vector for our transmitter, v sub t. And our direction of propagation is still going to be k hat. Okay, so our Doppler frequency in this case, f sub Doppler, you got to combine the effects here. We said for the receiver is going to be minus direction of propagation times v sub r over the wavelength. And for the transmitter, it's going to actually be plus k hat dotted by vt, because the wave is actually leaving the transmitter. So you do a little sign change there. That's also lambda. And in fact, these are basically common terms. So let's get those out. We could actually write this as k hat. Oh, and I got to have a k in there too. Wave number. Wave number, k hat dotted into the difference between my velocity of the receiver vector minus velocity of the transmitter vector minus velocity of the receiver vector divided by wavelength. And so what's the worst case Doppler scenario? Is basically where the receiver is moving directly towards the transmitter in a collision course, and you're sending the wave along that collinear line. That's the highest Doppler shift. The lowest Doppler shift is the opposite, right? The receiver and the transmitter are moving away. That shifts the tone lower. Now, there are configurations, keep in mind, that your receiver and your transmitter can be moving at a very large speed. But if those directions are orthogonal to one another, if Vt minus Vr is orthogonal to the direction of propagation, you don't get a Doppler shift, no matter how fast they're moving. Kamal, do you have a question?
Oh, yeah. I thought we canceled the wave.
Let's see. Did we cancel the wave? Oh, yeah. If I put lambda in the denominator, I got to take k out. Thanks for catching that. Mind is moving a little faster than the rest of me. We already took that into consideration. Thank you, Kamal.
Isn't there a dependence on the distance between the two objects as well?
No, not for Doppler shift. There's no dependence on distance. It's all about the angles that you make with relative to the transmitter, the direction of propagation, and the receiver. So that's one of the nice things. So it doesn't matter whether you're communicating to Jupiter or Uranus, or if you're doing a low Earth orbit satellite, It's all about the directions that things make with respect to one another. In fact, if you don't like vectors, you can actually write this as velocity of the transmitter. And what is the dot product basically? It's basically the cosine of the angle that two vectors make. And so you're going to write this as cosine theta t over lambda. And of course, theta sub t would be the angle that this makes with the velocity of, or the direction of propagation, minus v sub r cosine theta r over lambda. And theta sub r is the angle that basically the direction of propagation makes k hat with the velocity vector v sub r. And so if you ever want a really kind of a rough back of the envelope calculation of what you'd expect the Doppler shift to be, you just assume that the cosine is 1, right? Because this is never going to get larger or less than, never going to get larger than 1, never going to get less than -1. So your velocity over the wavelength is a nice rule of thumb for predicting how bad your Doppler is going to be. If you can satisfy your comm link within that range, you know, all the filters are set up so that the signals can slide around that much, then you're in good shape. And so let's do a quick calculation just to get some numbers around this concept. So let's say we have trying to estimate the Doppler on a GPS satellite. Doppler shift. And this will just be a back of the envelope estimate, just to get some ideas about how fast things are going. So we know that a GPS satellite is at a radius of 26,000, roughly 500 kilometers from the center of the Earth, which means according to our circular orbital mechanics equation, the velocity of that transmitter is equal to Kepler's constant over that radius. Kepler's constant for the Earth is about 4 times 10 to the 14th meters. Plug in our radius, capital R, here, and we get that a GPS satellite is moving at about 3.9 kilometers per second, almost 4,000 meters per second. That's pretty quick, you know? A lot of meters to cover. Now, what is the frequency of GPS? So one of the most common ones, at least the one that your handheld receiver operates at, is about 1,575 megahertz. Which, if we plug it in, divide that into the speed of light, we get a wavelength of 0.19 meters, about 20 centimeters, about yay long. Yay long. So based on that, the maximum Doppler that we could possibly sustain on this link would be the velocity of 3,900 meters per second over our 0.19 meters of wavelength. That's about 20 kilohertz, which is substantial as far as Doppler shifts go. Compare this to a terrestrial case. Let's say we were operating a 19 megahertz cell phone link, 1900 megahertz cell phone link. And we were on, say, the bullet train. That's probably the fastest you could possibly be on the ground and, you know, still communicate. Let's just get a rough order of magnitude estimate. For the bullet train, let's say it was traveling at about 200 kilometers per hour, which is about 55.6 meters per second. And let's see, you know what? The frequency is a little bit higher than GPS, so the wavelength's a little bit smaller. Wavelength's about 0.16 meters. But our maximum Doppler frequency, if we calculate with the same formula, is going to be about 352 hertz. Much, much smaller than it could potentially be on a satellite. Now, keep in mind that for our GPS signal, we didn't estimate any geometry effects in this, right? Chances are your satellite's never going to be going exactly away from you or towards you. The worst case scenario is probably when it's kind of in its circular orbit on the horizon. So, but also remember, this is also an estimate of maximum Doppler displacement. So this could be up or it could be lower. And so about twice that could be the conceivable range that your system would have to operate under. Just to get you some feels, you see we're about 2 orders of magnitude up in Doppler. And that's just for Earth satellites in mid-Earth orbit. Low Earth orbit, it gets a little bit dicier because they're a little bit faster. And they can actually get some of those really acute angles that are obtuse angles. Acute if it's coming towards you, obtuse if it's going away. And lead to those extremes in Doppler. And things get really dicey when you start about orbiting planets around orbiting spacecraft around other planets. There's a really famous story. Does anybody know the Cassini mission? It was a mission to Saturn back in the 90s. What? Yeah, that was part of the mission. It had the probe that it shot over into the surface of Titan and took a couple pictures, I think. And so there were several different scientific missions for Cassini, and that was one of them, the mission to Titan. And it looked at it did some atmospheric experiments for Saturn as well.
Saturn and Titan both.
Yeah. Yeah, so, and I know Professor Steffes worked on some of that mission. He tells a story about how the people that were designing the radio for the Cassini mission, they were Italian. And they accidentally forgot to take into account the Doppler shift. And the thing about Jupiter is that it's a very large planet and very massive. It has a huge Kepler's constant. And so you've got to orbit, I forget what a Jovian orbital period, but it's actually really low. You're going around this giant planet, but you can do an entire revolution. We're around Saturn. Saturn is also very massive, and it has a very large Keplerian constant. And you go around in several hours. It's very quick. And so think about it. You're leaving and then coming back, and then leaving and then coming back. You're going very fast, and you can actually shift, hundreds of kilohertz, even close to a megahertz. That should be a good test question. What is the Doppler shift on Saturn? I think there is a previous test question on that topic. Oh, yes.
We can derive this just from